This video is going to cover the solutions to the tutorial problem based on the question, how does a street lamp work? Problem 1. We're asked how many electrons would you need to add to a sphere to give it a charge of -2 times 10 to the minus 10 coulombs. So to answer this, we'll need to use that the charge is equal to the charge on an electron times the number of electrons. So the charge on a single electron is minus 1.602 times 10 to the minus 19 coulombs, and let's let n be the number of electrons. Now the charge we're trying to get is minus 2.00 times 10 to the minus 10 coulombs. So now we can use this to calculate n, the number of electrons. So n is equal to minus 2.00 times 10 to the minus 10 over minus 1.602 times 10 to the minus 19. Now these negative signs will cancel each other out. Now we can just solve it on the calculator. So we do 2.00 exp minus 10 divided by 1.602 exp minus 19. When we do that, we get the answer 1.25 times 10 to the 9. And this is the number of electrons, so that's electrons. Now the question goes on, how could you give the sphere a positive charge? So to give it a negative charge, we add electrons to it. To give it a positive charge, we can't actually add protons to it because it's very hard to get single protons. They tend to have electrons with them. So the easier way to get a positive charge is to remove electrons. So to get a positive charge, we remove electrons from the sphere. Problem 2. In this problem, we've got two spheres. Sphere A and sphere B. And these spheres are separated by a distance r. And we're given different charges on sphere A and sphere B and different distances r. And we're asked to calculate the force that sphere B exerts on sphere A. So we'll need to use Coulomb's law, that F is equal to K Q1 Q2 on R squared, and K is Coulomb's constant, which is equal to 8.988 times 10 to the 9 Newton meters squared coulombs to the minus 2. So in part A, we're told that A has a charge of +1, so Q1 is +1 coulombs, and B has a charge of +1 coulombs, so Q2 is +1. So F is equal to 8.988 times 10 to the 9 times 1 times 1. And the distance in this case is equal to 2 meters, so this is over 2 squared. So solving that, we get 2.2 times 10 to the 9 Newton. Now what we have to do is work out whether it's attractive or repulsive. In this case, both these spheres are positive, and so there's a repulsive force between them because they have the same charge. So this is repulsive. For part B, we again substitute into this equation. So we've got F is equal to K, which is 8.988 times 10 to the 9. And now in this case, sphere A has a charge of 1 coulomb and sphere B has a charge of -1 coulomb. So we put 1. And once again, they're separated by 2 meters, so we put 2 squared here. So once again, this is 2.2 times 10 to the 9 newtons. But now as this one's positive and this one's negative, there's an attractive force between them. So sphere A tries to move towards sphere B. Part C. Sphere A now has a charge of minus 2 coulombs. So once again, we're substituting in F is equal to 8.988 times 10 to the 9 times the charge on A, which is the 2 coulombs, times the charge on B, which is half a coulomb, over the distance between them, squared, which is 3 meters squared. So solving this on the calculator, we end up with 1.0 times 10 to the 9. But now they're both negative, so we've got negative and negative. So as these charges are the same, they're going to repel each other. So this will be repulsive. And so finally, part D. Once again, we substitute in. We have F is equal to K, which is 8.988 times 10 to the 9 newtons. Now, the charge on A is minus 0.75. The charge on B is equal to 3.0. We don't need this negative sign. That will be taken account of in whether it's repulsive or attractive. And the distance between them in this case is 1 meter. So we've got 1.0 squared. So solving this one on the calculator, we get 2.0 times 10 to the 10 newtons. And in this case, A is negative and B is positive. And so they've got opposite signs, and so this is attractive. And so that's how we solve problem 2. Problem 3. We're asked to describe the differences between conductors and insulators and give 2 examples of material that fit into each of these categories. So conductors. So conductors have electrons that are free to move and so are able to conduct an electric current. And examples: metals such as copper and gold, and a non-metal example is graphite, which is made up of carbon atoms. So graphite's able to conduct a current as well. Now insulators charges are not free to move, and so insulators prevent the flow of an electric current. So examples of this, we've got wood, we've got paper, glass, rubber, are some of the common examples of insulators. Okay, problem 4. We're asked to calculate the current flowing through a wire if 2 times 10 to the 20 electrons flow through the wire in 1 minute. Now to calculate the current, we've got that we need the charge over the time. So the time is 1 minute, so that's going to be 60 seconds. So now we need to calculate the charge flowing through the wire. So the charge will be equal to the number of electrons times the charge on an electron. So we're told that we've got 2.0 times 10 to the 20 electrons, and the charge is 1.602 times 10 to the minus 19. Now we don't need to worry about the negative sign here. electrons have a negative charge, but that will just determine in which direction in the wire they will flow. It won't change the magnitude of our answer. So solving this on the calculator, we get 32.04 coulombs. So now we can substitute in here. I is equal to 32.04 divided by the time, which is the 60 seconds. And so solving this, we get 0.53 coulombs per second, which is measured in amps. So 0.53 amps. Problem 5. We're asked to calculate the current flowing through this circuit. And so we're given a circuit diagram. We've got a power supply with a V is equal to 1.5 volts. And we've got a resistor here with a resistance of 100 ohms. So to answer this, we're going to have to use Ohm's law. V is equal to IR, where I is the current. So we can rearrange this to write I is equal to V on R. And now we can just substitute everything in. So V is equal to 1.5 volts and the resistance is 100 ohms. And so solving that on the calculator, we end up with 0.015 amps. And that is how we do problem 5. So with problem 6, we're given a more complicated circuit diagram. So we've got a power supply, which is 12 volts here. We're given a slightly different symbol for the power supply, but it's the power supply. And then we go through 2 resistors. So resistors can either be drawn as squiggly lines or as boxes, like this. So here we've got R1 with a resistance of 200 ohms and R2 with a resistance of 400 ohms. So part A asks us, are the resistors in this circuit in series or parallel? Well, the current comes out of the power supply, it all flows through R1 and then it all flows through R2. So this tells us that these resistors are in series. Part B then asks us to calculate the voltage drop across R1. Now there's a number of ways that we could do this. One way would be to look at the relative resistance. As this one has twice as much resistance as this one, the voltage drop across R2 must be twice the voltage drop across R1, and so we'd have 1/3 of the voltage drop across R1 and 2/3 across R2, so 4 and 8 volts. That's one way to do it. We're going to do it a slightly different way. What we're going to do is calculate the total resistance in the circuit. We can use that total resistance to calculate the total current, and then we can use that total current. We know the total current flows through every resistor, so we can use that to get the voltage drop across each resistor. So the total resistance is just the resistance of R1 and the resistance of R2. So this is equal to 200 plus 400, which is equal to 600 ohms. And so the total current from Ohm's law is the total voltage over the total resistance. And the total voltage is 12.0 volts and the total resistance is 600 ohms. So solving this on the calculator, we end up with 0.020 amps. And so now we can work out the voltage drop across resistor 1. So V1 is equal to I1R1. This current flows through everything, so this is 0.020 times 200. Solving that on the calculator, we get 4 volts. So part C asks us to calculate the voltage drop across R2. So we've got V2 is equal to I2R2. I2 is just the same as I1 at 0.020 amps. That flows everywhere. R2 is 400, and so this gives us 8.0 volts as the voltage drop across this second resistor. For part D, we're asked to calculate the current flow through R1. We've already done that. I1 is equal to 0.020 amps, and part E to calculate the current flow through I2. So I2 is equal to 0.020 amps. And so that's how we solve that problem. Problem 7. In this one we also have a circuit. We've got a power supply here, and then we've got a resistor here, and another resistor here. So we're told that this has a voltage of 20 volts. This one here is R1 with a resistance of 100 ohms, and this one's R2 with a resistance of 200 ohms. In part A, we're asked, are these resistors in series or in parallel? Well, the current comes out of the battery here. Some of it goes through R1 and some of it goes through R2. So it's got a choice about which path it wants to follow. So this is a parallel circuit. Now in part B, we're asked to calculate the voltage drop across R1. Now in parallel circuits, we know that we've got the same voltage drop across all the parallel parts of the circuit. So as these are the only components here, this 20 volt voltage drop occurs across R1 and across R2. So the voltage drop across resistor 1 is equal to 20 volts. Part C asks us to calculate the voltage drop across resistor 2. So once again, we've got the full voltage drop across that resistor, so 20 volts. Part D asks us to calculate the current through R1. So we know that I1 is equal to V1 on R1, just from Ohm's law. So this is 20 over 100. And so this is equal to 0.20 amps. And in part E, we're asked to calculate the current flow through R2. So I2 is equal to V2 on R2. V2 is the 20 volts, R2 is the 200 ohms. So this is equal to 0.10 amps. And that's the solution to problem 7. Problem 8. We're told that we're given a 12 volt battery in a torch and the resistance is equal to 4 ohms. So V is equal to 12 volts and the resistance is equal to 4.0 ohms. And in part A, we're asked what current flows through the globe in the torch. So we can just use I is equal to VR from Ohm's law. And so we've got 12 divided by 4. And solving this, we get 3 amps. And then in part B, we're asked what power is used by the torch. Now, we know that power is equal to the voltage times the current, VI. So we've got 12 volts and the current is 3 amps, so this is 3.0. So this is equal to 36 watts is the unit for power. So that's the answer to problem 8. Problem 9. If an appliance uses 28 watts, so the power is equal to 28 watts, and it's on for 3 minutes, so T is equal to 3 minutes, we're asked how much energy does it use. Now we know that power is equal to energy over time. And so energy is equal to power times time. Now in this case the power is in watts and we need to get the time into seconds. So we've got 28 watts and the time is 3 minutes, which is 3 times 60 seconds. And so this gives us 5,040 and the units for energy is joules. So 5,040 joules is the answer to this one. Except that we should probably only give it to one significant figure, so we can write it as 5,000 joules. Problem 10. In this problem, we're told that electricity bills use kilowatt hours to measure energy rather than joules. So to get the energy usage of an appliance in kilowatt hours, so energy in kilowatt hours, you simply multiply the number of kilowatts used, so that's the power in kilowatts, by the number of hours, so times the time in hours. And in part A, we're told that a light globe uses 24 watts of electricity, so P is equal to 24 watts. And it's on for 5 hours, so T is equal to 5 hours. And we're asked how much energy does it use in kilowatt hours. So to get the energy in kilowatt hours, we do the energy is equal to the power in kilowatts. Now we've been given the power in watts, so to get that into kilowatts we need to divide it by 1,000. So now this is in kilowatts, and then we times the time in hours. And now solving this on the calculator, we get 0.12 kilowatt hours. Now part B says if it costs 29.5 cents per kilowatt hour, how much will it cost to have this light on for 5 hours each evening for a year? So the cost will equal to the total energy used in kilowatt hours times the cost per kilowatt hour. And so the total energy used, each evening we're using 0.12 kilowatts, but we do this all year, so for 365 days. And now the cost per kilowatt hour is $0.295. So solving this, we end up with $12.92. So that's how much it costs to run this light every evening for a full year. And finally, problem 11. We're told that blue light with a wavelength of 475 nanometers, so that's equal to 475 times 10 to the minus 9 meters, is shown onto a piece of gold with a work function equal to 5.1 electron volts, which is equivalent to 8.2 times 10 to the minus 19 joules. Now we're asked, are any electrons released from the surface? So to release an electron from the surface, this photon coming in must have enough energy to overcome the work function. So we need energy of photon greater than work function. So what we're going to need to do is work out the energy of this photon. Now to do that, we'll need to use E is equal to So to do that, we're going to have to use E is equal to HF, where H is Planck's constant, which is 6.626 times 10 to the minus 34. But we're not told about the frequency of this photon, we're only told about its wavelength. So we're going to have to use an additional equation, C is equal to F lambda, where C is the speed of light and lambda here is the wavelength. So this tells us that the frequency is equal to C on lambda, which is equal to 3.0 times 10 to the 8 over 475 times 10 to the minus 9. So solving this one on the calculator, we get 6.316 times 10 to the 14 hertz. And so finally now we can substitute this frequency into this equation. So the energy is 6.626 times 10 to the minus 34. That's the H times the F, 6.316 times 10 to the 14. And solving this, we get 4.18 times 10 to the minus 19 joules. Now this is less than the 8.2 times 10 to the 19 joules, which is needed to overcome that work function. So this means that no electrons are released from the surface. So part B then asks us, well, what is the maximum wavelength of light that will release electrons from the surface? So what we'll need to do is work out what wavelength do they need to have so that they have this amount of energy. This is the minimum energy that will let them be released from the surface. So we need phi is equal to HF, and F we know is C on lambda. So this will tell us the maximum wavelength we're allowed. So rearranging this, we've got that the maximum wavelength we're allowed is equal to HC on the wave function. So this is equal to 6.626 times 10 to the minus 34 times 3 times 10 to the 8 over the over the work function, which is 8.2 times 10 to the minus 19. And so solving this, we end up with 2.4 times 10 to the minus 7 meters, which we can write as 240 nanometers. And so that solved that problem, and that's finished the tutorial.